Hello, calculus fans. Let's take the series where we're summing from n goes from 1 to infinity of 1 over n to the p, and we'd like to know for what values of p does this series converge. Now p can be any number we like, so we're going to try different values of p and see what we get. Notice that if p is less than 0, then the limit of the terms is infinity. If p is equal to 0, then the limit of the terms is 1. And in both cases, we can say that the series diverges by the test for divergence. Remember that the terms have to go to 0 before it even has a chance. Now, when p is equal to 1, we're specifically talking about the harmonic series, and we proved that that series diverges. Now, let's take a look at what happens when p is bigger than 0, but p is not equal to 1. So we're going to let f of x equal 1 over x to the p, because we're going to try to use the integral test. That function is definitely positive, continuous, and decreasing, so we can apply the integral test. We're going to go ahead and compute the integral from 1 to infinity of 1 over x to the p dx. And remember that p is not equal to 1. That helps us to compute an antiderivative. So we take our integral, rewrite it as a limit, and now that's an easy antiderivative because we can think of 1 over x to the p as being x to the minus p. Add a power, divide by the new power. And so we end up with this expression here. Now that limit exists when p is bigger than 1, because in that case you have m raised to a negative power, and so that would go to 0. It does not exist when p is between 0 and 1, because now that exponent on m will be a number that's bigger than 0, and so that would go off to infinity as m goes to infinity. So really, the only time that we found out that this integral converges is when p is bigger than 1. All right, that gives us a new theorem and a new test. This is the p-series test. The series n goes from 1 to infinity of 1 over n to the p, that converges if and only if p is bigger than 1. Now I'd like to illustrate the p-series, and I'm going to probably abbreviate this PST, p-series test. The series 5 over n cubed, that converges. It's a p-series. In this case, p is equal to 3, which is bigger than 1. But if we do the sum of 1 over the 4th root of n, that diverges, since that's a p-series with p equal to 1/4. Think of this 4th root of n as being n to the 1/4 power. I should point out that the 5 in the numerator of the first series doesn't really matter. It doesn't really change the fact that it's a p-series. You can always bring a 5 out in front. Okay, that's all for now.